So this is the first recitation I'm holding for this semester. So in the future, this is how I like to structure my recitations. I don't have a problem set prepared today because, well, we haven't really had that many problems yet, but we certainly soon will. It's better, so I'll try to come with things prepared. So like topics that people have asked me a lot of questions about, or things that people are not yet quite getting. But also, it's very helpful if you come with questions of your own, either general or specific. And so my personal teaching philosophy is I would like you, so whether you're working on a problem set or a quiz, I don't want you to just, well, quizzes you don't get any help whatsoever, so you're on your own there. Just pray for the Holy Ghost. But I would like you to spend just a little bit struggling first, not to the point where you're banging your head against the wall, but so that you actually start thinking about it, because then when you ask for help the second time, then it will actually stay solidified. So don't bang your head against the wall, but don't just say like, okay, here's your problem set, show me how to do everything on it. Does that make sense? And then the last note I want to make is that Mariana and I are probably going to try to do a recitation type review on Friday mornings from 7 to 8 in the morning. So that way you can get help before the quiz and freak out less, hopefully. And also remember that there are 4 different quizzes. Well, they're the same quiz really, but they're 4 different problem sets. So that way you're not like copying your neighbor or freaking out if you're looking at your neighbor. Just don't freak out. Anyway, what would you like to go over? What is not clear? What are you just curious about?
Could you go over like lumos stacking, homos stacking lumos? Or
Yeah.
That goes?
I'm gonna try to take pictures of this as we go along so I can actually put it in a nice PDF. And I'll post this on YouTube later today, so you have access to that. So from homo to lumo. So first of all, let's figure out how to identify these. So the homo is the highest occupied molecular orbital, and lumo is the lowest unoccupied molecular orbital. And in order to identify these, we have to look at the orbital energy diagram. So I'm just making this up for simplicity's sake, but this is actually the molecular orbital energy diagram of benzene. Don't worry about where it's coming from because we're just identifying things for now. So say we have something like this. So remember the lowest one here is the lowest energy. As we go up, we increase in energy. And so the homo is really interesting because you think lumo is lowest energy, homo is highest energy. It's actually the opposite. Homo is always less in energy than is the lumo. So the highest occupied one is the orbital with the highest energy level that still has an electron in it. So in this case, nothing, nothing, nothing. Ooh, we've got something here. So this right here would be our homo highest occupied molecular orbital. And then the next one up, that would be our lumo. And it's okay to have 2 or more orbitals that are identified as the homo/lumo if they're at an identical energy level. Does that make sense? And so if we change this, let's see how to take a picture. Say we take one of these electrons, or let's just take two of them, and we excite them up here. Now this one right here is the HOMO, and this one on top is the LUMO. Make sense? Hold on, someone's asking if recitation is still going on. Yes. In the tutorial. Okay, so how does that relate to chemical reactions in general? Oh, yes?
Sorry, just a question. When do you excite the electrons? Like, when does that happen?
That'll happen. That's specifically referring to light.
Okay.
The excitation of electrons happens when it receives a particular delta E, change in energy, in the right amount. So if you look on the visible spectrum, like down here we have infrared. You don't need to know this particularly. We've got microwaves. Unless you take physical chemistry, then you'll have lots of fun and heartache. What scientists have discovered is that on the spectrum, where we can't see and where we do see, even though the wavelengths are very, very small part on the orders of like nanometers, which is like billionth of a meter, it still has to be in exactly the right amount. So when we're going from here to here, it's gotta be, say, like 28 joules of energy, which is totally off, but it has to be exactly that amount in order for it to jump from one orbital to another. And when we actually excite the electrons, we actually say that the energy becomes quantized, which means that the energy levels are small and discrete. So it's like climbing a set of stairs. You have to climb each one separately. You can't like climb halfway up and say, oh, I've climbed halfway, I've gotten all the way there. You either up there or you're not. Does that make sense? Small and discrete. So that's the whole basis of quantum mechanics, is that the idea that energy is very small. It's not just continuous, it's very small and precise. So going back to HOMO and LUMO, in terms of chemical reactions, this is going to dictate basically all of chemistry. So a guiding principle of chemistry is that chemicals will seek a lower energy state. And also they're going to try to move around as much as possible. Well, they're going to try to move around as much as possible while expending the smallest energy possible. Lower energy state using as little energy as possible. So going back to the example we had in class with ammonia attacking, which sounds very gruesome, but it's not. Attacking HF, forming H3NH plus. And F minus. So looking at the orbital energy diagram for ammonia. Let's see, it's sp3. By the way, when he draws it like this, they're not like cute little H's, and they're not like smiley faces either. They're just electrons. And technically we are supposed to include the spin by putting an up and a down arrow, but that doesn't super matter for this, not for this concept. And so that was the NH-sp3 sigma bond. Then we had the 3 up here, which was the NH anti-sigma bond, and then we had the non-bonding pairs. And then for HF, what we had was this fluorine is also sp3 hybridized, and we had the one sp3hf sigma bond. Ooh, running out of room. We had the HF anti-sigma bond, and then we had the 3 lone pairs. NB for non-bonding. So you see what's happening. So first of all, we have to identify what the HOMO and the LUMO are in order to figure out what's happening with this reaction. So HOMO, so it's always going to go from, the order of attack will always go from the HOMO of one molecule to the LUMO of another molecule. So the HOMO is really the attacking species, or really the electrons, and the LUMO is the receiving end for electrons. So HOMO, we see that the ammonia, the lone pair of electrons on ammonia, was attacking the HF over here. So right here, this is the HOMO. Make sense? And then right here, so whenever we're moving electrons, remember, according to the Pauli exclusion principle, we can only have 2 electrons per orbital. So it is possible for these electrons to move up here through excitation, but then there wouldn't be any reaction. So we have to take these electrons and put them up there. So whenever we do any chemical reaction, we have to go from a filled orbital to an empty orbital. Just take a picture of this really quick. And so you might be thinking, but wait a second, isn't it unfavorable to put the electrons into an anti-bonding orbital? Well, if we're talking about the molecule by itself in isolation, then yes, we wouldn't want to go from up here to here. But remember, whenever we combine 2 orbitals, we're always going to get constructive interference and destructive interference. So what does that look like? So first, let me draw the final state for each of these molecules. So now this is all sp3, nitrogen, hydrogen, sigma, 1, 2, 3, 4, 5, 6, 7, 8. Then we have the anti-sigma for NH. And interestingly enough, for fluoride, we have, this is still going to be sp3 hybridized, but it's not going to be making any bonding or anti-bonding pairs. Why? Because it's not bonding to anything right now. So that's how the final state looks like, but we need to figure out like what happened. Freaking, why do people call me? Okay, I'm gonna erase this part of the board. So you see here we're taking a non-bonding, and this is still an sp3. It's just not a bonding orbital because it didn't combine with anything else. But here we're taking, so the sp3 looks something like this. sp3 from the nitrogen hydrogen bond. Now, there we go. So this is taking the sp3, non-bonding pair of electrons on the nitrogen, and we're comparing it with the anti-sigma on the HF. So the anti-sigma looks like this. And again, we'll get the destructive interference, we'll get the constructive interference. And so remember that for constructive interference, it's got to be in phase. And the destructive interference is out of phase. So when we go from here to here, we're actually going to combine this end, the in phase, with this right here. Here, let's do it like this. So that way it works out. We're going to combine this end with this end. Wait. Yeah, that's right. And then we still have the anti-sigma one over here. And then this one is simply going to stay as sp3 and the two 1s's. So this is not the end state of what's going on. This is what's happening as we're pulling the sp3 non-bonding electrons into the HF anti-sigma bond. Eventually they'll drop back into their sp3s, like those configurations I drew earlier. So just what I'm just saying is this is the transition state. It's happening in between. And so again, going back to the Y, that we're trying to obtain a lower energy state using as little energy as possible. The HOMO and the LUMO are the smallest energy levels apart that goes from filled to empty orbit. If we try to go from filled to filled, nothing would happen. It'd be like that helium dihelium molecule we saw where it would jump up into the antibonding and then just basically fall in on itself. So HOMO to LUMO is the lowest energy pathway for the reaction to move forward. Yes, Natalie?
Maybe it's not a big deal, but I'm just a little confused about your shading, why it's only half.
This should probably be the full thing.
Oh. Okay.
It doesn't particularly matter so much as to the shading. You just have to make sure you're consistent with yourself. Because really, it's the electrons are moving back and forth between either ends. And notice that as we move from whether we did constructive interference or destructive interference, we still maintained the same node we had originally. One node here, one node here. But here we had to create a node because we went to antibonding. Yeah?
So how do you know like what to draw and what the shape should look like?
Basically, so we're only going to be working with p orbitals and s orbitals. So the s orbital just makes so the sp3 you see is like this, right? It's basically just going to make this one bigger. So it's like inflating a balloon.
And is that for sigma or?
This is for, yeah, this is for sigma bonds.
Okay.
Pi bonds do not hybridize.
Are we going to need to identify when it's in this kind of middle phase where we're transition? Or are we gonna just need to identify like the end?
Probably
This is
just the
this
end. This is just for illustration purposes. Okay. Does that make sense? Yeah.
So why is that HF bond like set up like it's destructive?
What, this one right here?
Yes.
That was the antibonding orbital we saw over here. So yeah, we have to go from filled to empty, and the only empty one available was the sigma star. I mean, technically there are other orbitals that we could access, but they're way higher in energy. So in Chem 101, you probably learned about like D and F orbitals. And I actually will move over to the periodic table over here. It's not impossible for these molecules to access lower orbitals. It's just to go from like oxygen all the way to whatever PO is. Ooh, I'll name it after myself, Polson. So from oxygen to Polson, that would take a ton of energy. So it's easier just to go from like oxygen to sulfur in terms of orbitals. Does that make sense? Okay. So I think I've covered that in good depth. And I think, let me take a picture of this really quick. All right. So is this making sense to everyone? Yeah.
So what is the purpose of attacking? Why is that so important for us to understand?
Well, because this is how molecules form.
Okay.
Without this homo-lumo interaction, there can basically all atoms would just exist as atoms. There would be no molecules.
Okay. So you showed us this another molecular orbital where it had 4 on the bottom. How did that happen? Is it taking one of the orbitals and forming a new one, or?
Oh, you mean at this end state over here?
No, like earlier you had erased it.
Was it with F minus?
I think so, yeah.
Well, yeah. After this in between state happens, it'll collapse back down into those 4. So for F minus, it'll just collapse back down into the 4 sp3 orbitals that we saw.
Okay.
And how that happens, I'm not exactly sure, but I'm pretty sure that this is the transition state. Okay.
When you say it's like sp3 hybridized, are we just told that, or are we supposed to know, like?
Let me tell you the simple way to tell if it's hybridized or unhybridized. Is it hybridized? So the simple way to tell for carbon and nitrogen and oxygen and fluorine, the electrons that will take on a hybridized state are sigma and lone pairs. So single bonds and lone pairs. And what doesn't get hybridized are pi bonds. So double or triple bonds. So let's just go through a couple examples of that. So HF, we've got 1, 2, 3 lone pairs plus 1 sigma. So we start out with sp, then we go to sp2, then we go to sp3 because we're adding another p orbital every single time. So here we count up 4, so we go from 2, 3 to 4. Because 1s, 1s2p, 1s2p. So that right there is sp3. This 4. Now say we take cyanide, like that. Looking at the carbon, we've got 1 sigma bond, and we've got 1 lone pair. That counts up to 2, so that's going to be sp hybridized. We do have the 2 pi bonds, but the pi bonds, remember, do not have to hybridize in order to come together. And then with this nitrogen, it's going to be the same thing. We've got 1 sigma, we've got 1 lone pair, that's 2, so it's got to be sp hybridized. That's a way you can identify how. Well, who was it that asked the question? Was you, right? No. Yeah. So that's a way how you can identify what the hybridization state is of these 4 molecules. And you can also use this for like sulfur and phosphorus as well. But then we start getting up into like sp4, sp5, sp6 kind of stuff. Does that clarify it?
Yeah, thank you.
Okay. So, I guess the next question I have is, so I think does anyone else have questions on orbitals? How they work, why do we care? So if you want to, we can move on to some problems from the problem set if you want to. If you've already taken a look at that. The thing is, I don't want to so if you want me to do practice problems during recitation, I'm happy to do so. It's just I just don't want to like do all of them and then people just like, oh, I'll just watch the answer. Does anyone have a copy of that, by the way? I don't know. Not a hard copy anyway. So at one point, let's see. So 3 we really haven't gotten into yet, but number 2 is what we just talked about right now. So since we've already struggled through it, because you're like, what? I don't know. I'm trying to be funny. Let's see. What would be a good one to do? I'll do the 3rd molecule in the set. Let me just draw that out really quick. And so to make this a little bit easier, let's expand the carbon-hydrogen bonds. We'll get into this a lot later, but it's very common to eliminate carbon-hydrogen bonds because they cluttered the page. So I'll label these molecules as 1, 2, 3, and 4, because the problem says label the hybridization state of every atom other than hydrogen. So, looking at number 1, what do we have attached to this carbon right here?
4 single bonds.
4 single, 4 sigma bonds. So what hybridization state does that have to take? The one with, the one that combines all them together. And so on your sheet, you can just draw an arrow to it like this and write sp3. You don't have to like do it separately like this. I'm just doing that to keep it neat. Number 2. So this, what is the, now looking at this carbon, what does this one have? It's got 1, 2, 3 sigmas. And what else does it have? It's got the 1 pi bond. And so the pi bonds don't get hybridized. So we only have 3 that are relevant. So we need the orbital that has 3 parts to it. So which one is that? sp2. The nitrogen, whatever, nitrogen, I already labeled it. So what's on that nitrogen? Got how many sigma bonds?
2.
How many lone pairs? 1 lone pair. What else? So remember, the pi doesn't count, but the lone pair does. And so 2 plus 1 is 3. So what state does that have to take?
sp2.
So you see, this is actually not too bad. And you'll notice right here, for the 2 atoms in the pi bond, both of them need to have the same hybridization state. So then moving on to the last one. What is that? That carbon? So that one's easy, we just have 4 sigma bonds. This becomes sp3. Okay. Make sense? Because we do have 3 bonds, but one is a pi bond, and that doesn't count in hybridization. So if you want to visualize it, you can just pretend like that's not there for a second. It does count. It does count for lone pair.
Could you point out like the sigma bonds on the, because I get what the pi bond is, but then there's 2 sigma bonds, but there's only, do you count that as like both sides?
So with the double bond,
Yeah.
first one's sigma, the second, and every other one is pi.
Yeah, okay.
So it's really not too
Okay.
bad.
I get it.
Hooray. Okay. So I think, is that,
One more question. So on the homework, how should we write it?
oh, like I did right here.
Just like that?
Yeah, just point an arrow, sp3, sp2, sp2.
Okay,
That's the easiest way to do it.
sounds good. But we
Okay.
don't need to have all of like the sigma bonds and pi bonds.
No, this analysis I have over here,
That's
no.
just to help.
That was just to help teach you.
Perfect, thank you.
Okay. So I think we've basically covered orbitals. We've covered it to a good degree. Does everyone want to stay on that topic, or do you want to? Well, we really haven't talked about anything else this week. Let's see. Yes.
Do you mind if we go over some like information about pi bonds?
Sure.
Our lecture yesterday or last time?
Yeah. So I think the real question you're asking is why are these not hybridized? And for fun, just so you know why we call them single sigma and pi double or triple bonds, is because sigma is single, pi is product, 2, 3. So So that's why in math classes, if we can remember that far, why we use capital sigma for sum and capital pi for product. Pi product sigma sum. It's pretty fun. So the reason why the pi orbitals, or the orbitals that make up the pi bonds, do not need to get hybridized like to sp2 or sp3 or something like that, is because that they're at the same energy level. So we'll take the carbon double bond example with 2 sigma bonds to just anything. Could be hydrogen, could be a halogen, doesn't matter. Could be tungsten. Let's do tungsten now. So the original state, how do I want to do this? So before we form this bond, the original configuration, I'll go from atom to molecule. That makes the most sense. So the base electron configuration for carbon was this: 1s, 2s, 2p, and then the carbon was exactly the same. So we could take these, well, let me finish out this 2p. This is one of the reasons why we have to do hybridization. If we were to combine both of these orbitals right now, you would think, oh, well, I can just take this p orbital, pop it in there, this p orbital, pop it in there, and we're all happy, right? But that's not the case. Remember, with the Pauli exclusion principle, we have to fill the empty orbitals before we fill them up all the way. So these p orbitals would actually end up just going right there, and we wouldn't form bonds between the two. Well, we form one, but we'd still have 2 empty ones. Okay. Oops, and there's a third one right here. Before this happens, though, we have to actually excite an electron from the 2s to the 2p. So now we have 2p, 1, 2, 3, 2s. 3 of these, 1s, the 2s, and 2 of the 2p's will mix together to become the sp2 that we see. Those mix to become sp2. And this one is all by itself. So we've got 3 sp2s, 1 2p, and so that's the hybridization of each carbon before we combine them together.
Where did you get the third one? Because you circled 2, but then you said 3 sp2s. How did you get that one?
Well, because it's 1, 2, 3.
Oh, okay, thank you.
So whenever the number of atomic orbitals we have always has to equal the number of molecular orbitals that we have. It's got to stay conserved. That is an essential rule of quantum mechanics. What am I trying to do? So you understand how that becomes sp2, right? Okay, now moving on. So now we have, why do we need the sp2 in the first place, you might be asking? Well, the 1s with the hydrogen is too low in energy to get up to the 2p orbital over here. So if we hybridization brings the 2p lower and the 2s higher, so we get an averaging out of energy. But overall, it creates a lower energy orbital for us to use. So, but we're worried about the pi bond right now. Carbon 1, carbon 2. Whoops. And now you can see we can nicely combine these ones we still have the 1s hydrogen. Times 2. This should be down here, but I'm just drawing it because I'm just trying to illustrate it. So the one, now that we have it hybridized, the 1s, the two 1s's from the two hydrogens we saw attached to these can fit snug as a bug down here. And same over here. We can fill those half orbitals. So this goes back to what I was trying to say earlier, where we'd fill this orbital because it's empty. So it'd be 1, then 2, 2, 2. Now we have all half-filled orbitals. And with all half-filled orbitals, anything we combine, when we do half orbital plus half orbital, half-filled orbital plus half-filled orbital equals covalent bond. So we took those, we popped them down here, popped it down here, and then the two left over, the sp2 from both carbons, those can combine together. And that accounts for the 3 sigma bonds we see. But for as far as the 2p orbitals, those are already the same in energy, unlike the 1s and the sp2 orbitals that we saw earlier. So these ones can just sneak in just like that, and we're all happy. So does that make sense now? Oh, someone's texting me, what time is the recitation? Almost over.
So is that 2p the pi bond?
Yeah, this
Okay,
2p.
when they combine together?
Yeah. So all the sp2s will make our sigma bonds, and the 2p orbitals will lead to my pi bonds. Someone's asking when recitation is over. And by the way, if you want to text me through Remind or through my regular phone number, I don't, it doesn't matter to me. But it was really interesting to see, like, okay, like, if you want to sign up, text at Chem285, and then it's like, and then 5 minutes later, 110 people joined. So it looks like a lot of people like that service. Okay. Oh. I'll take a picture of this and send it out to everyone as well. You can take a picture still if you want to. Before I erase all of it. Okay. So, any last minute questions about orbitals? Yes.
Can you explain on pi bonds, like when the 2p come together and you have construction or constructive interference, why is it important that the electron density, like when he was using the flanking thing?
Why is it
What's
important
the
that they
importance of
flank?
that? Yeah, because he said the electron density flanks the nuclei when they come together, the 2p's.
Yeah.
Orbitals come together, why is that important?
Let's just draw those out really quick. Yeah. So we're accustomed to thinking that electrons are purely in between the two nuclei, but remember that the electron is seeking out the proton. If it's right here in the middle, that's the so think of it like this, where it's like the hypotenuse of a triangle, which is the longest side. The nuclei are sitting right here and here. It wants to get closer by switching over there to a shorter side of the triangle. So the reason why it's flanking back and forth is because it's seeking out that electron. Flanking meaning it's right over the nucleus. That's as close as it can get. And also it helps to realize that this helps us visualize how electrons work in general. They're moving around at an extremely fast pace. And so if we specifically restrict them to in between the two carbon atoms, then we're basically saying they're not going anywhere else, which is not true. Electrons can actually move all over the atom. Does that make sense?
I can't really visualize that. The long hypotenuse, it's trying to.
So I'll draw it again like this. So here we have our two, so I'll just draw it. Here we have our two electrons, right? When it's in the middle, like that, well, if we strictly sit them in the middle, then they're the furthest distance away possible from the protons as they can possibly be. Does that make sense?
The protons are.
The plus sides.
Yeah.
Yeah, the nucleus is the proton. Set of protons. And also, if we stick them in the middle right here, they're going to want to repel each other anyway. Opposite charges attract, like charges repel. So if we just stick them in the middle right here, I'll get to your question in just a second, then we're putting the electrons closer together, so they're more likely to repel each other. But if we spread them out like this, then we also get them closer to the nuclei, and we get them further away from each other.
Okay, that makes sense.
So it's like two roommates who don't really like each other that much. Okay, what's your question?
Okay, so I think it has to do with what you just said, but so if the electrons are like that, aren't they like further away from the protons? And then it's
Yeah, they're
not?
further away, which is why we want to bring them to the outside. Did I say closer?
I don't remember.
I meant further away.
So is that how they're actually, or are they like more?
They're more like this.
Okay, so that's how they actually.
Yeah.
Okay.
And that's
And-
what flanking means?
Yeah. Well, flanking is more like flailing, where it's like moving back and forth. The orbital is the entire space that the electrons can occupy. The electrons are never just sitting in one spot. Well, they're within like a same region of space, but they're not like at one point within that region of space. They're continually moving back and forth between those two endpoints. So it's kind of like an ellipse, sort of. Or maybe like a NASCAR race car, where the two cars on opposite sides of the track are always on opposite sides of each other. Good questions. I think that's probably good for today, unless there are more questions. So next week, I'm gonna try to get I'm gonna force them to. I'm going to get an actual room scheduled, because then I can actually use my iPad and like write a nice PDF of it, and then just send it out as is, and I can record it at the same time. What else is I going to say? If you want a copy of the notes, it's okay to like take pictures, or either ask someone else directly, or you can email me and I'll send you like a PDF of it. the thing is with like getting notes for missed days, he just doesn't want it to like you to send it out to everybody possible, because then that kind of destroys the purpose of coming to class. Because one person, Natalie.
Oh, no, after.
Oh. Because the first day I met him, he basically told me, like, you can do whatever you want, just don't bag on the class. And don't say negative things about me. So I probably won't, even though I kind of want to. Is that still recording?
Yeah.
I need to delete that.